Miao Lobsters is a chain of 4 lobster restaurants. They buy their 2-pound hard-shell lobsters at 3 different locations. Since the spot prices and transportation costs differ from location to location, the manager made a table of possible profits each restaurant will get by purchasing the lobsters from each location. The table also includes the maximum supply of each location and demand of each restaurant. Write down the linear programming problem for this model. Define your variables, xij. Alright, before you go on, you should first make sure that the supply and the demand is met. Remember, if the demand is more than supply, then you have to make extra dummy variables. 3 plus 4 is 7 plus 250, that's 950. 200 plus 250 is 450. And then these two add up to 500. 500 plus 450 is again 950. So both the demand and the supply add up to 950. That means supply is equal to demand. That's good because that means we don't have to put any dummy variables. If the supply is bigger than demand, still you don't have to do any dummy variables. But if the demand is more than supply, then we have an example where you have to put dummy variables, dummy origin actually. Okay, so first let's say xij. Now we used to put numberings like 1, 2, 3, 4, 5, 6, and so on, and put that xij as number of lobsters. Here's purchased by it's L, the location to the restaurant. So the first number should be the location, and the second number should be the restaurant. And we'll have the xij to be number of lobsters purchased by restaurant J from location I. And we'll just use these numbers 1, 2, 3 and 1, 2, 3, 4 for each. That's still okay. That's another convention that people use. If your numberings are already there, 1, 2, 3 and 1, 2, 3 like this, you can just use those as your ij. Alright, first let's start with the origin nodes. Remember, origin nodes, you always need the inequality. So we have for L1, you have x1 bought by restaurant 1 plus x1 bought by restaurant 2, x1 3, x1 4. These are all the sum of the lobsters bought by the restaurants, and they have to be less or equal to the total supply that this location 1 can provide, which is 300. You see this 300. Okay, so for L1 that's 300, so that's what we have. And then we go on to the L2, location 2 to restaurant 1, location 2 to restaurant 2, location 2 to restaurant 3, 2 to 4, and this time location 2 has 400 as its maximum supply. Location 3-1, location 3-2, location 3-3, location 3-4 has to be less or 250. Okay. Now for the destination nodes, we need equalities, and destination nodes are some of these quantities, and that has to meet the demand, which is 200. So for R1, it's x1 to 1, location 2 to restaurant 1, location 3 to restaurant 1. All of these are what restaurant 1 will be receiving, then they have to add up to the demand. So that's what we have. Okay, x1 2, x2 2, x3 2. These are everything that's going to restaurant 2, and then I have to equal to 250. x1 3, x2 3, x3 3, 3. Then I have to add to 350. x1 4, x2 4, x3 4 has to add up to 150. Okay, and then finally the objective function has to be this one. Objective function should be basically everything that's in here multiplied by the numbers, these numbers as coefficients. So it's 5x11, 7x12, 6x13, 6x14. That's the first row. Then 7x21, 5x22, 4x23, 5x24, and now the last row, 6x31, 7x32, 8x33, and then 5x34. Okay, and you have to maximize. Actually, that's actually the important thing. Maybe I should write this in red. You have to maximize the objective function in this case because it's profit. You want to maximize the profit. And then don't forget, every time you define xij, always write down xij bigger or equal to 0. And that's it. That's the linear programming. Using northwest corner method, find a feasible solution. Also compute the total profit of the restaurant chain. Okay. So northwest corner means the top left is the first one to be used. So you use 5 and you spend as much as you can. So the supply is 300. What the demand is 200. So you use 200 because that's the most this restaurant can give. Now once this is gone, this is met, there's no more to give here, so these are all deleted. And then this one, since it used 200, now it's left at 100. Okay, let's write it here, 100. Okay, and then you always try to do the top left. That's the goal. So the top left this time is the 7, and you put the maximum you can use, which is 100, and this now becomes 150 left. And since now you've used everything, these are all gone. Okay. Now the remaining rectangle is here. The northwest corner is this one, and you use 150. You give all it can demand. It demands 150, so meet the demand, and that will leave you with 250 here, and that's going to delete this. Now this is left. You use 250, all of them, to get rid of this. It's not completely gone. 350 minus 250 is 100, and because all 250 is gone, this is no more needed. And this is the rectangle. In this case, the northwest is here, and we use 100 to meet all the goals. And then what's left is 150, and that 150 is used over here, and then that's gone. Okay. Now, since demand is equal to supply, as you can see, after getting the feasible solution, you get 0, 0, 0, 0, 0, 0. All right, so that is the feasible solution. Now, in this case, the total profit for the chain would be just simply number of lobsters that you will be purchasing times the profit that you will get out of it. So in this case, 5 times 2, which is 1,000. 7 times 100 is 700. Then 5 times 150 is 750. 4 times 250 is 1000. 8 times 100 is 800. Then 5 times 150 is 750. Okay. So what is this? This is 1450. And then this added up as 3,450. And these two add up to 1550. So adding the two, we get $5,000 as the profit. Okay, so we see that this feasible solution gives you 5,000. Now, of course, the northwest corner just gives you a feasible solution, and it's usually very far from the optimal solution. I mean, if you get lucky, sometimes it might give you the optimal solution just by pure luck, but in most cases you get a number that's far from the total profit. Okay. Now C, using the maximum method, find a feasible solution. Does this yield bigger total profit? Probably yes, but let's see. See, the goal is to maximize profit, so you want to use the highest number. When we are solving transportation cost problems, we use to look for the lowest number because we want to reduce the cost, but in this case you're trying to maximize. So let's use this 8, that's the highest in the table, and you use as much as you can, 250 going to 350, so you're going to put 250 here, and that's going to leave you with still 100 demand. And since this used up all 250, this is 0, so now these are all invalid. Okay. Now let's look for the next highest number. Here we have two of them. We have 7 here and 7 there. And in this case, it doesn't matter which one you use. So if you have same numbers, just like when we were doing the minimum method, you may end up with multiple possible solutions. Okay, multiple correct solutions. Let's choose this one, 7. And since you have 300 and the demand is 250, we're going to give 250 as the maximum demand. So all the demand is met. That means this is gone. And 300 minus 250 will leave you with 50. Okay. And then now these are the remaining ones. Among the ones that are left, this is the biggest number, 7. And it's 400 going to 200, so I guess we can go give 200. Leaving with 0, that's gone. And this will be now 200. Now notice that even if you start with 7 first, it would have been the same. And so in this case, we still see the solution is unique so far. Now the remaining numbers are these 4. And you could either put your 6 over here, use this 6 or that 6. And in this case, really, you can't have non-zero numbers for both. So here it's really it really depends which one you choose. So there are two types of correct answers. One which you might want to use this 6. Another one where you use this one. Okay, let's use this one. So we're going to use up all 50 because that's all it has, and it's going to still leave you with a 50 as demand. And because all of it is used and 0 is remaining, this is no longer in effect. And then you have 200, and then 5 is bigger than 4, so we use 5. Use 150. That's gone. So this is now met. And then 50 is left. And all that 50 can be used to meet this demand 50. So that's gone. And that's gone. And then that's it. All right. So these are the numbers that we use. Oh, why did I scratch this out? This is okay. So this is optimal solution, and let's see if we can get higher total profit from here. So the total profit is 200 times 7 is 1400, and 250 times 7 is 1750. 50 times 6 is 300. 4 times 50 is 200. 8 times 250 is 2000. And 5 times 150 is 750. These add up to 3150. That's 500. This is 2750. And 3250 added together, we have the total profit of 6,400. Okay, so the answer is yes. This does yield bigger profit. Okay, rather than 5,000, we now can make 6,400. Of course, if you use the Excel solver, you may even do better, because the maximum method gives a better solution, but you can't guarantee that it gives you the real optimal solution. All right, draw a network diagram for the solution you found with the maximum method. Okay, so I'll have to go back and forth. We have L1, L2, L3 as the suppliers, and you have 4 restaurants, R2, R3, R4. Let's go back and see what it has. So first, L1 sends 250 to R2 and 50 to R3. So let's do that. R2, 250, R3, 50. Okay, and then L2 sends 200 to R1, 50 to R3, and 150 to R4. Okay, 200, 50, and 150. Okay, and then R3 sends only 250 to R3. And that's it. That's the network diagram representing the solution.